Chapter 17, Part 5, Inferences about a population mean when the population standard deviation is unknown. We're going to continue on with doing some more examples, and then we're going to hopefully get into doing a paired t-test. So we continue on with looking at some examples. We're going to call this the octane example. A consumer advocacy group claims that the octane in a manufacturer's gasoline is less than their stated 87.0. The testing organization takes a sample of 40 and finds that the sample standard deviation is 0.5 and the sample mean octane is 86.86. Is there enough evidence to support the claim of the manufacturer at the 0.05 level of significance? Or another way that you could look at it is there enough evidence to support the claim of the consumer advocacy group that says that the octane is less than 87? Well, first we look at the assumptions. Well, the assumptions for t-test are met. We have a simple random sample. It has a size of 40. So as we know by the central limit theorem, our sampling distribution is approximately normal. It has a mean of mu, but the standard error that we need, since we don't have sigma, is s over the square root of n. That's why we're in a t-distribution with 39 degrees of freedom. So we're going to state the null and alternative hypothesis. The manufacturer claims that their gas has 87.0 octane, whereas the consumer advocacy group says that it's a little less than that. The significance level at which this test is at 0.05, given in the wording of the actual problem. The first thing that we're going to do is calculate the test statistic. Remember, it's x bar minus mu naught over s divided by the square root of n. Well, we know from right here that in our null hypothesis it's 87, and from the actual problem we found out the sample mean and sample standard deviation. The sample mean was 86.86 in the sample of 40, and the standard deviation, sample standard deviation, was 0.5. So our test statistic ends up being negative 1.77. By using Minitab, we can find that the p-value is 0.042. Since our p-value is less than alpha, we have sufficient evidence to reject the null hypothesis. So our conclusion would be, at a 0.05 significance level, there's sufficient evidence to support the claim that the octane in the particular manufacturer's gasoline is greater than 87.0. We would use Minitab. The command would look like this. It's a 1T, and we input our data, our N, our X bar, and our S. So our N was 40 in our sample. The X bar, remember, was 86.86 with a sample standard deviation of 0.5. We want to test the null hypothesis value of 87, and it's a left-tailed test, so the alternative is -1. When we hit enter, this is what comes out. And what we care about is the T and the P. That T is the test statistic, calculated test statistic, and that p-value is our p-value. So since that p-value was less than alpha, we reject the null hypothesis, so there's sufficient evidence at a 0.05 level of significance to support the consumer advocate's claim that the octane in a manufacturer's gasoline is less than 87. So now it's time to look at the matched pairs T procedures. The reason why we use this is we can compare two treatments. Subjects are matched in pairs, and each treatment is given to one subject in each pair. Before and after observations on the same subject also calls for using matched pairs. To compare the responses to the two treatments in a matched pairs design, apply the one sample T procedure to the observed differences, one treatment observation minus the other. The parameter mu is the mean difference in the responses to the two treatments within matched pairs of the subject in the entire population. That would be a matched pairs procedure. So let's take a look at this example. The pollution index measurements were recorded for two areas of the city on each of 8 days. At a 0.05 significance level, is there sufficient evidence that the average pollution levels differ for the two areas of the city? So we have area A and area B. What we want to see is if there's any difference at all in these two areas. So we're going to calculate the difference in their pollution rates. So that's what that third column is, the A minus B. So if we were in Minitab, we'd have C1 being area A, C2 being area B, and column C3 would be the difference of those two. Looking at the p-plot and the box plot of this data, we see that the data looks relatively normal. There is no major deviations from normality. So we're going to say that the population is approximately normally distributed. That is the differences. So and there's no outliers from our box plot. So with the data, we have a mean of 0.10113, that's the mean difference, and the mean standard deviation, sample standard deviation, is 0.1960. We can now calculate our test statistic or use Minitab. So we're going to start off doing it by hand. The null hypothesis is that the mean is 0, there's no difference in pollution levels, and the alternative is that there is a difference. The significance level we were looking at was 0.05. And the test statistic, we calculate our mean difference, which was 1.0113, minus our null hypothesis value, which was 0, divided by the sample standard deviation, divided by the square root of our sample size. We get 14.594. That's a big test statistic. So when we calculate the p-value, look how small it is. It's teensy-weensy small. So we're going to say that we're going to reject that null hypothesis. So there is a difference between these two areas. So at a 0.05 significance level, there is sufficient evidence to support the claim that the average pollution levels do differ from the two areas of the city. Now this is what we would do in Minitab to get the answer. We'd put the one level in, let's say, column 3, the other level in column 4, and put the differences, let's say, in column 5. This is how we do it. We'd say let C5, let column 5 be the differences between the values in column 3 minus the values in column 4. Then we're going to do that T, the 1T on column 5, the differences. We're testing 0, that's our null hypothesis value, and the alternative was 0 because it was a two-tailed test. And there's our output. And in Minitab, you see the p-value being 0.000. That means it's virtually 0. So you would write that the p-value is less than 0.0001 is how you would write that up in a paper. Now, if we're going to do a 95% confidence interval, we'd have to find out the confidence level, the critical value. We'd look for degrees of freedom of 7, and down the 95% confidence level to find the critical value. So we go 7 down to 95, and that's why we got the 2.365. And we're going to multiply that by S, the sample standard deviation, divided by the square root of 8. We're going to take that margin of error, subtract it, and add it to the mean, and we get our 95% confidence interval. We estimate the mean difference of the pollution index in area A and B is 0.8474 to 1.1752 index points with a 95% confidence interval. And the last thing we're going to talk about is the robustness of T procedures. The T confidence intervals in tests are exactly correct when the distributions of the population is exactly normal. No real data are exactly normal. The usefulness of these T procedures in practice, therefore, depends on how strongly they are affected by the lack of normality. The confidence interval, or significance test, is called robust if the confidence level, or our p-value, does not change very much when the conditions for use of this procedure are violated. Now, except in the cases of small samples, the assumption that the data are a simple random sample from the population of interest is more important than the assumption that the population distribution is exactly normal. Sample size is less than 30. You can use the T procedure if the data appear close to normal. No outliers, it's single-peaked and rather symmetric. If the data are skewed or if outliers are present, don't use the T distribution. For large samples, the T procedures can be useful, even for clearly skewed distributions when the sample is large enough, roughly 30 or more. So here's an example where it's so skewed that we can't use the T procedure. Looking at this stem plot, the data there is very skewed, so that we can't use the T procedure for that. When N's distribution is so close to normal, we can definitely use the T procedure. So this concludes Chapter 17. Bye.